So next, he's going to tell us about his work on navigating dynamic noise landscape for variational quantum algorithms. Right. So this will be about doing computation with reasonable enough fidelity in the presence of transient noise. Yep. And I will let you take it away.
All right. Thank you. Okay, so the previous speaker spoke about quantum error correction, and that is useful in the long term of quantum computing, but that requires a lot of qubits, like like Sara just asked me. So it's also useful to have algorithms which can work reasonably well without quantum error correction. So they can benefit from error correction, but they can also be useful in the noisy regime as well. And one such family of algorithms is these variational quantum algorithms. So it's useful to find other ways to reduce errors in qubits so that these algorithms can produce like useful results as well. So in this work, we propose QISMET, which identifies, is the first to study and mitigate transient qubit errors on long-running algorithms like these variational algorithms. And while it is sort of tailored to these variational algorithms, some of these learnings are useful in other long-running algorithms as well. So I'm going to start with a brief introduction to variational algorithms and this work. So variational algorithms can be thought of as navigating an optimization contour to find a global minimum, which is the answer to the problem at hand. And you usually start from some initialization point and navigate through this contour to hopefully find the solution. But quantum machines are noisy. So what happens is that there are these things like noise-induced local minima and barren plateaus, which makes finding this optimal point very challenging. Right? So there are multiple solutions to navigate this. For example, you can find good initialization, which is the work I spoke about yesterday. But even after you find good initialization, the contour might still be pretty noisy. And so you want to reduce the effects of noise. This is, of course, not a new challenge. People have been working on different noise mitigation approaches to reduce noise. So for example, but the sort of limitation in prior work is that they assume that the noise characteristics are static in some sense. So they assume that that the noise they would observe for a VQA algorithm is something like this blue line you see over here, which is the effect of qubit noise is seen on the algorithm, but it's sort of static in some sense. And so they use some error mitigation algorithms to reduce the effects of these errors and hopefully achieve this orange line. On the other hand, if you look at how the dynamic noise characteristics actually affect these algorithms, you can see that they significantly affect the way gradient estimations are made and therefore make convergence and the accuracy much worse than what prior work usually assume. So in this work, we propose QISMET, which is tries to identify some of these dynamic instances of high noise and removes them so that we make the blue line more of a reality, so that other error mitigation techniques can then be used to bring this blue line close to the orange line, which is the end goal of finding very accurate solutions. So I'll discuss a little bit of background on variational algorithms. So again, the idea is to find this global minimum in this optimization contour, and this is useful for chemistry problems, optimization problem, which is the focus of the next talk, as well as other areas like drug design, finance, and so on. And the idea is that each point in this optimization contour is a quantum state, which is generated by a quantum circuit, which is known as an ansatz. And the different gates in this ansatz, like the purple ones you see here, can be tuned to different angles, and they take different angles on that block sphere, which you see at the top. And then you use like a classical optimizer to control these different values so that you can produce different objective function values in the space and hopefully go towards that, the objective minimum, the global minimum. Now, noise can affect different parts of this quantum circuit. You can have noise at the qubit initialization, at the single qubit gates, at these entangling gates between qubits, just decoherence of the qubit state happening over time, and also errors during this measurement phase. And of course, this is not specific to variational algorithms. It's common to all quantum circuits, and there's been a lot of prior work to address some of these issues, including from ASPLOS and other architecture and systems conferences. But the sort of main assumption or the fact that these methods use is that they assume that this noise information about these qubits is sort of known a priori, and some optimizations are made based on this noise information, which is known. On the other hand, if you look at this graph over here, this is a real qubit characterization for something known as the T1 time, and this T1 time is an estimation of the time it takes for a qubit to decohere from a one state to a zero state, and you can see from this graph that this can vary significantly for a single qubit over time. So you can see that over 60 hours, this estimation varies from 100 microseconds to 25 microseconds. And especially these points which are close to the bottom can be very detrimental to quantum circuits because they can significantly affect the fidelity of your circuits. And you can see an example of that over here. So this is some circuits we ran on an IBM quantum device. And you can see that, and these are the same circuit run over like a couple of hours in sequence. And you can see that there's significant variation in the fidelity or the output that these circuits are producing. Right now, when your circuits are low width, which means few qubits, and low depth, which means only a few gates, you might have a graph like the one you see at the top, where there's only a limited variation in the fidelity of these circuits. But on the other hand, if you look at the graph to the bottom, so this is a high width and high depth circuit, and you can see that the variation becomes much more significant because even if there is one qubit which is having a significant like a transient fluctuation, and if this qubit is on the critical path, then it can significantly affect the output of your circuit. And again, this is at a circuit level abstraction, and this affects all circuits. But this is even more detrimental when you look at the application level abstraction, right? Like for variational algorithms. So you can see here that this variational algorithm starts from this value of 1, and it's expected to converge to a value of around -5 on a noise-free machine. But the effect of both static and dynamic noise significantly affects this, right? You can see all these spikes over here, which are due to instances of transient noise. And this significantly affects the way that the gradient descent is supposed to happen. And this is because the objective function value estimations are significantly skewed, and this makes the gradient controller choose a wrong direction as to be optimal. And you can see that from the 100th iteration to the 500th tuning iteration, there is no progress being made by this circuit, right? Effectively, there's no progress made. And it is this that QISMET is trying to combat. And I'm going to give a high-level intuition of how QISMET works. So QISMET stands for quantum iteration skipping to mitigate error transients, which is fairly intuitive. So the idea is that, so this is an example of the baseline. So you have a quantum job, which is being run on the quantum machine. And this is running some particular some VQA circuits corresponding to, say, iteration I-1. So what QISMET does is that it repeats circuits from the previous iteration I-2, and that's what you see in purple over here. Now, the reason for this is that, let's say you move to job alpha, which is the next job, which is trying to run iteration I, right? So here you rerun iteration I-1 as well, which is a reference circuit for this job alpha. Now, the goal of QISMET is that the iteration I running in job alpha will be accepted only if the noise experienced by job alpha is similar to the noise experienced by job omega, right? And this would mean that there is no significant transient fluctuation happening in this job. And the way this is done is that by using this QISMET controller, which compares the outputs of the reference circuit I-1 with the original circuit I-1, and also using some information from I to decide if the noise in alpha is acceptable or not. And in this case, it is going to be deemed acceptable. So we go to job beta, which is running iteration I+1, and also using I as a reference to compare against alpha. Right. So in this case, it might be the scenario that this I is not acceptable because the noise is too high, that the output produced by the rerun of I is very different from what I was run earlier. And so we now move to job gamma, where this I+1 is being repeated again with the same reference circuit. And the number of repetitions is something which is controllable, right? In our work, we keep it fixed, but it is possible that you can do some profiling as to how long these burst errors might occur, and then set the number of repetitions based on that. And finally, in this example, this time it is deemed suitable for progress, and then we move to job delta, where you're running VQ at iteration I+2 and using I+1 as a reference circuit and so on. So I won't go into detail as to how this controller works, and there's a lot of detail you can find in the paper. But what I'd like to mention is that if you were designing this controller sort of naively, so what you would do is that you would just compare like I-1, the rerun, with I-1 original. If they're very similar, you would accept the result. And if they were very dissimilar, you would not. Now, that's how we started, but we found that this was actually not a very good method because a lot of iterations were getting skipped, and this is sort of deviates away from the fundamental goal of trying to make forward progress. So we instead came up with what we call this gradient faithful controller. And what we do is that let's say that we had some iteration I, which had this measured energy, which is shown by this green circle over here. And let's say that the iteration I plus 1, you see the measured energy, which is higher than iteration I. Right? Then we remove the estimated transient error fx, which is obtained by doing that comparison between the rerun circuit and the original circuit. And once we do that removal, we have this estimated energy for I plus 1. Now, suppose the estimated and the measured gradient are either both positive or both negative, which means that I plus 1 is relatively good or bad compared to I. Then we are ready to give a strong accept to this iteration and move on with it. Right? On the other hand, if the iteration I plus 1, the measured value is, say, has a higher energy compared to I, but the estimated value after you do this removal of these transient effects is lower than the estimated energy of I. This means that the measured gradient is positive, but the estimated gradient is negative. And this means that we are not sure if the ideal gradient is good or bad, which means we don't want to make progress based on these results, which means we give this a weak reject and we want to give it a major revision. So we will run this iteration again, and until hopefully we can make forward progress with good results. And so now looking at some results from real quantum machines, you can see that this is run on an IBM machine. You can see how QISMET is able to avoid these instances of significant transient error in sort of different scenarios. In the top figure, you can see that there are multiple instances of some transient error, which is still affecting convergence. And by avoiding them, QISMET is able to achieve significantly better results. And at the bottom figure, you can see just one instance of high transient error, which the baseline is experiencing, which is being avoided by QISMET. And again, therefore, it's able to make significant forward progress. Now, in the paper, we have many other results from real quantum machines as well, which you can look at. But we also did some simulated analysis because we want to compare like a lot of other methods. And this is tough to do on the real machine because we can't run all of these at the same time and make them experience the same transient error. So we built these transient error noise models and compared a number of schemes. And we found that the QISMET approach is very lightweight and is therefore able to make significant forward progress while significantly avoiding these major transient errors as well. So yeah, so I'm happy to talk about these other methods if people are interested. And with that, I'll conclude. So this QISMET is the first to study the effect of transient errors on VQAs and mitigate it. And essentially, QISMET works by avoiding these instances of high fluctuating noise. And by doing this, is able to achieve like significant fidelity improvements of VQA, and it also has usefulness in other non-variational algorithm approaches as well. So yeah, thank you, and happy to take questions.